I'll get started here. Let me begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class and this time we have to meet and study your creation. Just pray that you would be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me pick up on the proof that we were almost done with. And the next direction I need to prove is that 2 implies 1. So 2 implies 1. So 2 is, so we're going to assume that F, and I'm going to give it some details here, PQR, all right, is path independent on U, which was an open connected, at the moment, subset of R3. All right. And I'm trying to establish that F is in fact conservative. All right. Now, F being conservative, we define to mean that it's equal to the gradient of a potential function, right? So our current goal is to show that there exists a function from U to the reals such that the gradient of little f is equal to PQR. That's the task that's in front of us. All that we have to work with is the path independence of the vector field. So what we do is we use the path independence to define f, all right? And the definition that I'm going to give to little f is a proposal. F of, let's say f of r is equal to, like, the integral from, let's say, r naught to r of f, well, let's find, yeah, f dot dr, all right, where, well, let me start out with c. C of r down here is a notation, where c of r is a path from r naught to r, all right? So I guess my first thing I should say up here is pick a point. Let's pick a point, r naught, which is going to be, find r naught. X naught, y naught, z naught is an element of U, right? We can do this, all right? We can do this because, well, it's a set, right? So it's got a point in it. So pick a point. That's your reference point. And the thing is, we have path independence, right? So we can just as well, we can denote f of r actually is essentially the integral from r naught to r of f dot dr. Why is that? I mean, so what I'm saying is, why is this single valued is my question, right? Do you guys understand why this defines a function? So I'm saying integral from r naught to r is shorthand for the integral over CR, right? Path independence gives us that this is single valued, all right? So let me draw a picture for us. I'll imagine, just for the sake of Well, actually, let me not even draw you because, fine, I'll draw you. This picture's not in the notes, by the way. So here's like an idea of what U could look like, all right? It's an open set. It's got a fuzzy edge, all right? And what I need to do, right, in order to attain our goal is I have to give you an argument which shows that if we differentiate this formula, right, if we take partial derivatives of that formula, then we obtain a gradient which is PQR, right? So how can we show that? Well, so just to draw a picture here, I don't know where R naught is, it doesn't really matter, so it's here, let's say, okay? I want to study the change in this function at some point. I'll put it up here, x, y, z, okay? Now, the path independence gives me that any path that I connect these 2 points with gives us the same output, right? So if we want to understand how this, how this function changes in the x direction, it's helpful to us to, well, first of all, we can find like a path like this, and this point right here. So this joining point. Oh, rats. Let me just, oh, it's fine. I just got to do my notes. I think my notes have used R naught in different ways. So let's fix this now before I get further into this mess. Let's call this R1. Let's put ones on the reference point. All right. All right. So what I want to say is, in fact, I can find this point here, all right, which is actually going to be at, and so this point, over here would be, oh goodness gracious. So I'm picking this point over here, x naught, y, z. Now why can I do that? I can do this because this is an open set, so like, I can, the picture doesn't do it justice, but I'm inside the set. So I can pick a point also that's inside the set such that this line segment that joins them, which like this here and this here. So we can say that this is, let's say, Cx, and really it's Cx naught, yeah? Because it just goes to x naught, and then this here is the line segment which joins this point to that point, so I'll call that L sub x, right? And this, and I do mean for this to just be in the, like in the x direction. All right, so f of r is equal to the integral over c Cx naught of f dot dr plus the integral over L sub x of f dot dr. All right. Now let me be explicit here. L sub x, right? We could basically we can use x as a parameter for it if you like. It has y and z fixed, and x naught less than or equal to x naught goes over to x on that line segment L sub x. All right, so let me actually write down the formulas for it. So what I'm trying to claim here, guys, is that if we look at partial f partial x, which is partial x of the integral over this guy, plus the integral over Lx we can write down explicitly. That's the integral from x naught to x, all right, of p of t, comma y, comma z, dt. So here, like, to be more explicit, I have x equals to t for x naught less than or equal to t less than or equal to x. I'm sorry, I'm just, but I'm using x both as the fixed point I'm differentiating at. I'm varying in the coordinate. I'm sorry, this, like, it happened. But I'll probably, anyway, let me shut up. So the point here is that dy is 0 and dz is 0 and dx is just equal to dt along that line segment, right? So the line integral along L sub x, it just simplifies to the p component because we're not varying y and z along that line segment, right? And how about, is there any x dependence on the integral over the cx naught, like this part of the path that goes from R1 up to that joining point? That's 0, right? So all we have then is partial x of the integral from x naught to x of p of t comma y comma z dt, right? But what is that by the fundamental theorem of calculus? Part 1. It's what? By FTC1, this is exactly p of x comma y comma z. So that's 1/3 of a goal. That's 1/3 of our goal, which is to show that the x derivative of this alleged potential function works out to p. All right?
Why did you say the first part is 0 again?
Because there's no x dependence. X naught is independent from x. All right? Like x naught, we're just picking a point. So actually, like, we pick this point x naught y z close. It doesn't have to be close, but somewhere inside the set. We can do that because it's an open set. And then we look at a horizontal line segment relative to that point. How far that line segment goes doesn't depend on the center of the point. So that, in that sense, x is independent from x naught. And if you can do this for a horizontal line segment in the x direction, what can you also do? You can repeat this argument for what? Right. Exactly. So we can go, okay, so we can also start at R1, right? And we can go up to that point, whatever, x, y naught, z, right? And I can do this kind of deal, like an L sub y, right, over to the point x, y, z. And then, of course, if I call this thing, c y naught and L sub y, I have f of x, y, z equal to the integral over c y naught of f dot dr plus the integral over L sub y of f dot dr. But in a nutshell, what is dr along dy? Well, dr is simply equal to y hat dt in a nutshell. And we go from y naught less than or equal to t less than or equal to y. So this implies that partial f partial y is really partial y of the integral from y naught to y of q of x comma t comma z dt. Why is that? Because dr only is moving in the y direction along that line segment. Right? So, okay. Because of that, we only pick up on the change in the q component there, And then FTC part 1 does the job, right? FTC 1 says, well, you're integrating, you're differentiating an integral with variable bound. So lo and behold, you've got Q of x, y, z. And finally, we can go from the, the base point R1, and we can go on, we can go to our initial point, let's say x, y, z naught, and then we can look at a vertical line segment from there up to our point, arbitrary point x, y, z, right? And this time I'll call that CZ naught, and I'll call this L sub z, and I think you know where I'm going with this. F of x, y, z is equal to the integral along the curve that goes to z naught of f dot dr plus the integral over L sub z of f dot dr. Now this time, the L sub z has, my dr is simply dt z hat, right? And we're doing z naught less than or equal to z less than or equal to t rather, less than or equal to z. And so this implies that partial f partial z is the z derivative of the integral from z naught to z. What happens when we take the dot product of f with the r here? We only pick up on the z component, which we called r, right? And all right, so we've got r of x comma y comma t dt, and again by FTC1 we get r of x, y, z. To summarize, hence, thus, the gradient of f is equal to p, q, r, and we're done. Because we've shown the x, the y, and the z derivative are as they need to be. Yeah.
Does it actually have any time dependence, or do we just do something derivative?
Has any time dependence?
Or t, whatever t is. Since we introduced t, and then
Well, we integrate over t, so it's a variable which is used up in the integration process. So it's, FTC1 doesn't have a t dependence here. I mean, I guess if we write it in terms of t, integral from t naught to t of, f of u to u is simply equal to f of t. This is FTC1 back in Calc 1. I mean, okay, there I'm using u instead of t, but you see there's no u in the answer. There's only a t in the answer there because there t plays the role of the fixed but arbitrary variable that, the variable bound which we're differentiating with respect to. Yeah.
Can you remind us what path independent, like
Path independent.
Vector f to be path independent?
It means that the integral along coterminal paths are equal. So like, it doesn't matter whether I do, I've drawn these three different pictures so that it's less busy, but like if I try to draw them all at once here, I can also go from, just a second here. So I can go from, R1 over here to this point, right? And then I can do something like this. Or I can do, and I'm sorry, you can come in on, all right, so this picture is slightly heuristic, I suppose, or I can come in up here to this point, right, and I can come in like that. The point is that whether I'm coming in Cx naught or like Cy naught and then L sub y, or if I'm coming in Cz naught and L sub z, these three different paths these are three different ways to get to the point x, y, z, and they have to all be equal because we have path independence of the line integral. That's assumed. Yep. And it doesn't even matter, like, there's all kinds of other, right? We could just as well have done, like, whatever. I could have had a path that did this. Whee! Right? I could have done that to calculate the potential. But that wouldn't have helped us with our derivation, right? So we picked the simplest path that we can actually calculate the derivative of using calculus we already know, which is FTC1. But that's what this theorem is, though. This is the fundamental theorem of calculus part 1 as it impacts vector calculus. That's what's happening here. All right? So that proves the equivalence of 2 and 1. Now, so there's also like, corollary, if you like, proposition. Given f, which is conservative, well, I don't want to say conservative, which is, path independent, we can construct, right, the potential f of r is equal to the integral. Now I'm going to use r naught if you guys don't mind. r naught to r of big F dot dr, then f of r naught is what? Now that I've got past the proof, I'm going to use r naught as I usually do. So what happens if you integrate from the path which begins at r naught and just goes to r naught? You can just think of it as the stupid constant path. You go nowhere. The integral is just 0. All right. So by construction, this would be 0. So all right. This implies that the gradient of f, right, is equal to f. Physics, what do we do? Let's talk about physics for a second. You would say u of r is equal to the integral from r naught to r of f dot dr. Then you'd be wrong. This is not the potential energy due to the force F. If you want to calculate the potential energy due to the conservative force F, we are going to need to put a minus right here. All right, we need a minus right there. Then if we do that, that implies that the force is minus the gradient of the potential energy. So this is how potential energy U for conservative force F, how it works. That's how that goes. But we need the minus here in order to get that minus over there. Right? Now, in practice, I don't usually calculate potential for a given vector field with this method. I don't find that this method of calculation of F is usually easiest. Like most typically, to calculate the potential, I just integrate the P and the Q and the R to find the F, which, anti-differentiate the given components. That's usually what's easier to do, yeah.
We have to know all the physics equations.
Oh yeah, yeah. If I spend class time on it, it's definitely could be on the test. That's true. Yeah, yeah. So let's see here. Where was I? So I think I can erase this proof, right? So I wanted to. So I'm probably going to ask you guys to turn in surprise attack. I mean, not probably. I'm going to ask you to turn in surprise attack mission. What are we on? 10. Is that the next one? I got 11 on the top here. 10. There's 13. 11? I think it may be. Is it 11?
It's definitely.
It's 10? Definitely 10?
Because you gave us 4.
I mean, I believe you guys. I didn't. Trying to find my copy of 10 here,
Oh, it's 10.
Maybe you guys took all my 10s. Maybe I don't have a 10 up here.
You got mine.
I got yours. Anyway, so 10 is the next one. So tomorrow, I should collect that. So I wanted to talk a little bit about one of the problem types, or well, two of the problem types on that, before I go on to the next material. All right. I mean, I could show you guys an example of how we could actually calculate potential for a given vector field with this, if you'd like to see it. Let's see here. I think first I'll talk about the surprise attack mission stuff. If I can find my surprise attack mission. Give me a second here, guys. There's 11, 11, 11, 12, 12, 12, 12, 12, 13. This is not helping. 11, 13, 13. By the way, if you didn't get it already, you can get it up here at the end of class. Oh, 10, yay. All right, so hopefully at this point, calculating, like problem 1 is a gift, right? Problem 2, if possible, right? In problem 3, if possible, find the vector field which gives you a curl as given. Let me. Example 1. So just here's first of all a reminder. We should remind ourselves about some things we worked out the other day, right? We had 2 easy ones to remember. The curl of the gradient is 0. And we also learned that the divergence of the curl is 0. So there was a third more complicated curl of the curl that we used to derive Maxwell's, like the wave equation for light, but that doesn't matter. There's homework at the moment. Okay, so these we should keep in mind. These are helpful. So like example 1, consider if we have a vector field f, which is, well, excuse me, this doesn't. I don't think this doesn't help you with the surprise attack mission necessarily. Oh, maybe it does. Hey, this is probably like problem 4. So consider f, which is, I don't know, let's say minus y 0 x, just for the sake of discussion. What's the curl? What's the curl of this vector field? I'll do the determinant thing. All right, so what we got? We've got x hat times 0 minus y hat times, partial x of x minus, plus partial z of y, all right? And then plus z hat times partial x of 0 minus partial y of minus y. All right, what's that give us? We got ourselves a, looks like a minus y hat plus z hat, yeah? Oh, exciting, 2 components. All right, so this one, the curl is apparently 0, minus 1, 1. Okay? So I guess that's kind of like problem 1 on surprise attack mission 10. So here's a question. Is this a conservative vector field? In other words, does there exist f such that f is equal to the gradient of my potential function? Logically, is this possible? Is this permissible? The answer is clearly no. Why? If so, then, the gradient, the curl of f would be the curl of the gradient of little f, which is equal to 0. And yet, this is most certainly not equal to 0. So no, this is not a conservative vector field. It has a non-zero curl. Therefore, there does not exist a little f whose gradient is the given vector field. Does that make sense? I hope that makes sense. So that's the kind of logic that might help you solve problem 4. All right?
Is it not 0 because?
Because this is non-zero. It just takes one non-zero component.
Oh, okay.
If you had 2 zeros and one 0.000000000000000000000 here till next week, 1, curl's still non-zero. And like even the slightest non-zeroness in any component is enough. It spoils it. All right, so that's one thing. Example 2, suppose, all right, f has the curl of f equal to, I don't know, y minus x, 3z, and z. Okay? Let me throw in a z squared here just for kicks. Is this possible? If so, find f, right? That's like, questions what? I don't know. A couple questions on surprise attack mission are basically this format, right? Like questions 2 and 3 are like this, all right? So here, the hero of this problem is the divergence, right? This is a check, right? This is a check on whether or not it's even possible. Certainly if, so if we calculate the divergence of, the curl of f here, allegedly the curl of f, that's the divergence of y minus x, 3z squared z, right? Which is what that's minus 1 plus 0 plus 1. Oh, man. I'm going to square that z. There we go. Square that z. So then we've got a 2z. All right, there, I feel better. I wanted this to fail. Okay, so I somehow made it work out to 0 to start with, which is not what I wanted. So this is clearly non-zero, right? 2z minus 1, which is not equal to 0, therefore insane. All right, it's insane. You can't have that because we know that the divergence of the curl is equal to 0. This is a contradiction. The above is a contradiction. Right? It's a contradiction. All right, so if the divergence of the curl, alleged curl, works out to be 0, then maybe we could actually find a vector field whose curl is actually the given curl. All right, so let's look at an example like that.
Those identities, whatever we have, if those equal 0, does that mean it's conservative?
I didn't say that. It might be conservative. Now that's a good question to ask. Is it necessarily that they're conservative? Like, I don't know, actually. I haven't thought about that. Recently, anyway. I'd have to think about that. I don't think we have the technology. That's a good question to, file that question. Ask it again in 2 weeks. At the moment, all we can do is investigate. And so what we're going to try to do is, hopefully this one all right, so like example 3. Suppose we're given that the curl of f is equal to, I don't know, like y, we can do y minus x and 3, all right? Then, as you can see, the divergence of this, 0 plus 0 plus 0 is 0, right? So maybe there does, maybe there exists f for which that happened, right? Maybe it is the case. All right. Okay, so what is the curl? Well, the curl of f, right? I'm going to use the PQR notation if you guys don't mind. So the curl of f is partial q partial y wait a minute, second here. I need to write it out. P, Q, R. All right, so the curl. I do the Y, that's an R. Yeah. Partial R, partial Y, minus partial Q, partial Z, comma, partial, oh, just, yes, partial P, partial Z, minus partial R, partial X, partial Q, partial X, minus partial P, partial Y. So there's the formula for the curl of F, curl of PQR, all right? Now that's supposed to be equal to, in our current context, Y minus X and 3. Ooh, I made this problem way harder than your mission, like your surprise deck mission problem, right? We've got 3 non-zero things to match. This is annoying. Oopsies. So let's see here. I mean, what we have to do then is we have to solve partial R, partial Y, minus partial Q, partial Z, equals to Y, and we need to have partial P, partial Z, minus partial R, partial X, equals to minus X. And last but not least, we need partial Q, partial X, minus partial P, partial Y, equal to 3. Now, there's good news and there's bad news. The good news is we're going to be able to solve these. The bad news is we could all get a different answer and still be right. All right, there's like infinitely many different ways to solve these. So I'm just going to show you a way, all right? So like, how about this? I just insist on this being 0. I want this to be 0, okay? If I do that, that tells me that I should make R equal to like 1/2 y squared, right? That'll do it. All right, and then to solve this one, if I want to make partial P partial Z to 0, let's say, then that tells me that I want to make R equal to, 1/2 x squared, right? Now, to be fair, I could have added a constant what? Like in the first one, I could do what? Add a constant C1 of what? I'm partial integrating with respect to y, right? So this could have, in principle, had an x or a z dependence in here as well, right? And in my second one, I'm partial integrating with respect to x, so I could have had a y or a z dependence in there, and it wouldn't have fouled up what I was trying to do there, All right, and to get 3 for the last one, may I humbly suggest that we make partial p partial y be 0, all right? And if I do that, then that suggests to me that I need q equal to like 3x. And, possibly plus some constant of, well, apparently y or z.
How is gonna be like
Oh, but it's not. We're not done yet. So in order to continue this game I'm playing, the question is, can I have my cake? I mean, I've sliced off like 3 pieces of cake. Can I keep those 3 pieces and put them together? I mean, like the 3 pieces I'm talking about is I've assumed this is 0, and I've assumed that is 0, and I've assumed this is 0. Can we achieve all those things? Well, how about if we make P, all right, so like proposal, I suggest we just make F literally equal to my P, I will make 0. My Q, I will just make 3x. I don't care. I don't need the constant there. My R, I need both of these things. So I'm going to do 1/2 x squared plus y squared. I'm pretty sure this vector field has a curl, which is the one which is given.
So it would be equally valid to do something, set the others equal to 0 and solve out that.
That's very true. I could have instead imposed that partial r partial y was 0. And if I'd done that, I would have got that q was yz, or minus yz. You know, if I had said partial r partial x is 0 here, I would have gotten p is equal to minus xz. If I had instead imposed partial q partial x was 0, I would have obtained a p is equal to minus 3y. Let me explain to you guys the problem. What's the problem? Well, it's not a problem. It's a blessing and it's a curse, because you see the gradient, excuse me, the curl of f plus the gradient of any function g is equal to the curl of f plus the curl of the gradient of g. But what is the curl of the gradient of g? It's 0. That means I can take this answer that I just found and I can replace it with like partial g partial x, comma 3x plus partial g partial y, comma 1/2 x squared plus y squared plus partial g partial z, and guess what? That has a curl which is the same as the one which is given. What did I do?
No, I'm just asking. So you can just put any number in the place of partial g partial x.
Any function g, any function. You see how there's an incredible ambiguity in our choice of, like, working backwards. There's a stupid amount of flexibility here. There's not a unique answer. There's a multitude of them. Yeah.
Could you find a function g such that partial g partial x 3x plus partial g partial y and half x squared plus y squared partial g is equal to the same result that you would get if you set the other, like partial r partial y, partial r partial x, and partial q partial x? If you set all those equal to 0, could you find a g function that could swap between the two?
What you're really asking is it always the case that two of my different answers that I have obtained by my ad hoc method are always differing by a gradient? And the answer is I don't know. Yeah, I don't know. Maybe. That's another good question to file a for 2 weeks from now. It's a good question. So like, Jake is basically asking, does this account for all other possible answers? Are all other possible answers obtained by just adding a gradient like this? You know? Maybe. I don't know. I really don't know. All I know is that the answer here is not unique. And so that makes it hard for the grader, right? But not impossible, because one of the problems, it's impossible. The other one it is, right? And the one you have in the homework is easier because there's only one non-zero component. So you just have to basically, and the one in the homework, you could just set two of the components equal to 0 and work with the third remaining component to come up with the vector field whose curl is the given vector field. The surprise technician problem is easier than this. Yeah. Okay, so let us move on. So, let me do at least one sample calculation of this thing, and then we'll move on. I really do. I should show you at least one example of this potential formula thing in action. I'll do it for the stupidest possible vector field, which is the constant vector field, right? It's kind of fun. So let's find the potential. Let's see, where am I at? Example 4. Here we go. Find potential for f equal to, let us say, ABC, such that f of x naught, y naught, z naught is equal to a 0. All right? And so if we believe the proof, allegedly we can do this. F of r is the integral from my base point, x naught, y naught, z naught, where I want the potential to be 0, to my arbitrary point, x, y, z. And then I've got f dot dr. Now I need a parameterization of the line, and so Jacob, not Jacob, Joshua, we're going to use the line segment this time. Right? Like we're actually just going to go from this point over here to the point x, y, z. What's the parameterization of that? R of t is what? This is something we all must be able to do in here. The base point, the starting point, x naught, y naught, z naught, right? Plus t times the difference in the starting and ending point. So x minus x naught, y minus y naught, z minus z naught. There you go. That's the parameterization that has r of 0 is x naught, y naught, z naught, and r of 1 is x, y, z. So there you go. That's the parameterization of this line segment. Great. So let's do the calculation. We have the integral from 0 to 1 of ABC, right? Dotted with, what's my dr dt? It's the direction vector for the line segment, yeah? It's x minus x naught, y minus y naught, z minus z naught. That's the velocity vector. And of course, I have to integrate this over the time of the domain, the parameterization, which is from 0 to 1, you see. This is just a constant, and so the answer is stupidly a comma b comma c dot that difference vector, right? And so you can, well, we can work that out, right? What is the formula? We have a times x minus x naught plus b times y minus y naught plus c times z minus z naught. There you go. That is the potential function for the given vector field, the constant vector field, which clearly makes f of x naught, y naught, z naught equal to 0. And the gradient gives me x, y, ABC, right? Now, like I said, I don't really like this method of calculation. I don't think this is the best way to find the potential for this constant vector field. What's the best way to find the vector for the constant, the potential for the constant vector field? What should I just do instead of this? What would be smarter? How about if I just say, well, this is the gradient of f, right? And I just try to solve this directly. So if I face the music directly, I simply got partial f partial x equals to a, partial f partial y equals to b, partial f partial z is equal to c, right? And we can, those are constants, we can integrate, it's not a big deal. We immediately get f is equal to, ax plus c1, which is a function of y and z. We get f here is equal to by plus c2, which is a function of x and z for that partial integration. We get f is equal to cz plus the constant 3, which is a function of x and y this time, yeah? And then we take these three answers, right? And we think for a second, and we go, oh, okay. So apparently f of x, y, z is equal to ax plus by plus cz plus some constant, let's call it d, right? And then you can fit the constant, right? If you plug in f of x naught, y naught, z naught, and force it to be 0, then you're going to get your constant d is necessarily, minus ax naught minus by naught minus CZ naught, which would get us back to this answer. So I think the solve and fit is faster. Well, I don't know if it's faster, but I gravitate towards what I wrote in blue as a method of calculating the potential. I don't tend to actually use this much. But it is physically very important because this is how we define potential energy in physics, as the integral of the vector of the force field. All right, so there's an example for you. So next up, we are going back to 2 dimensions, all right? And we're going to be in 2 dimensions for a little while. So, I mean, that should make you happy. I think the proof I did at the start of class would have been like way clearer if I'd just done it in 2 dimensions. I probably should do that. Just do the proof in 2 dimensions, you know? But, oh well, it's too late. So in 2 dimensions, there are really 2 kinds of integration to think about for a 2-dimensional vector field. All right? We can think about the circulation of the vector field along a curve. All right? But we can also think about what's known as the flux of a vector field through a curve. And so I think the concept of flux of a vector field through a curve, that's a new concept for us. Let me draw a picture. So suppose you've got, here's some field lines. All right. Here's some field lines of a given vector field in the plane. So here we're given a vector field F, which has components P and Q for us, all right? And we want to define basically the flux. We have some curve, right? Like this maybe. And we'd like to define, we use this closed circle to indicate it's a loop that we're calculating. It's a closed curve. We'd like to define F. Well, here's the notation. F dot n vector ds. This is equal to the flux of F through the curve. Essentially, it's the number of field lines that go through the curve. All right, that's a way of thinking of it. Now here, the vector field has the flux is largest when the field lines, the integral curves of the vector field are going perpendicular to the tangent to the curve. All right, so like, where's this n I'm talking about here? So n hat. Let me make my picture a little bit different so that it kind of. Oh, forget the. Let me fix it here somehow or another. Let me do something kind of silly. I'm do this like this here. All right, then. So like, all right, there we go. So if that's my picture for C, all right. Then rats. I'll fix it eventually. Oh man, I can't help but go through that, can I? Dang it. All right, well, fine. Anyway, I'll eventually get past my thought. So the n is the outward pointing unit normal. So this is n. Maybe I should use n hat because I do intend it to be unit length, all right? So n hat, n vector rather, is outward pointing unit normal. All right. And, all right, so like, on the other hand, we could think about the tangent to the curve, right? And so this is an oriented curve. So it's, it's got some direction. Let's say this way. So the curve is going like that, all right? So if I draw the tangent vectors in here, what do they look like? They're like this, right? They're perpendicular to n, right? So here's my unit tangent, if you like. Right? So the unit tangent, we could, in terms of arc length, it's what? It's dx ds, comma dy ds, right? Unit tangent. I know it's the unit tangent because remember arc length parameterization has unit speed. So the velocity, the derivative of the position with respect to arc length is the unit tangent. Can you guys give me the formula for n? If this is t, right? If t is, that, how do you get n? What's n?
The same as capital N.
It is not. It is not. The Frenet normal points inward, but this points outward. Right? So it's not the same as the Frenet normal. No. Yeah.
Is it minus the Frenet normal?
Well, yeah, but what's the formula for it here in terms of dx ds and dy ds? Because we just need to rotate. Here's the vector. Rotate it. How do you rotate this 90 degrees in the right way? What is it? Like, what's the formula? I'll write down a formula. Is it not minus dy dx, ds rather, dx ds? Does that work? See if it works. All right, so if the tangent has, if dy ds is a little bit positive, right, then,
Did you just say that n dot t is 0?
yeah. Well, yeah. But what's the formula for it? If I think about, let's see here, this t right here, right, would be something, roughly, if I do it, directly here, like approximately, it's 0, 1, right? But the n should be what? 1, 0. So, okay, so I definitely don't, apparently I need to have the minus over there, right? All right, so let's see here. Let's try it out for, let's try it out. So down here, right up here, right? See here? We've got dx ds is negative. It's going to the left, right? Correct?
Yes.
And the normal has to point up.
Yes.
That's what we want. So there you go. That is the correct formula for the outward pointing unit normal. So what's the formula for flux? Well, the formula for flux, what was your question, Ruth?
I was just asking, if we did have the negative on the other one, would that mean that it pointed inward?
I think so, yeah. Yeah. So the arc length integral of the outward pointing normal component of the vector field, that's the flux by definition, is actually equal to the integral of the vector field, which I'm going to write out PQ, all right? P comma Q dotted with, well, my n was apparently dy ds comma minus dx ds, you see? And of course I got a ds here. Let's work that out. What we got? Well, we got the closed integral of p dy ds minus q dx ds times ds, right? So what is that? So in a nutshell, we have the integral over the curve of p dy minus q dx. And we also use the symbol phi for flux. So the takeaway here is that the flux integral, we can flux through curve C, we can integrate over C simply p dy minus q dx.
So where did you say that for simple?
Flux. It's the flux of the vector field PQ through C.
So is this just Gauss's law?
Is this just Gauss's law? Well, this is 2 dimensions. So, yes and no. I'll get back to that.